Okay, good afternoon to everyone. So, my AV is okay. Okay, thank you, Saksham and Abhishek. So, we'll start module 3. It is optimal system operation. So, whatever we have studied under module 1 and 2, that is mainly load flow studies, isn't it? That is the main thing we have studied. So, which is also required for this optimal system operation. Without performing load flow or power flow analysis, we cannot go for this optimal system analysis or optimal system operation because this is required. Okay. So that is the thing we are going to do it. Now, what is this optimal system operation? Here, system means it is a power system. Understood? Now you have to operate this one. Now you have to operate this one such a way that it should be optimal. What do you mean by optimal? See, we have to achieve a good result or better result. We should achieve better results, but it is not the excellent results. Understood? It is not the excellent or final results. Optimal results means it is not the excellent or final results, but we should get a good or better results. That is the meaning of optimal. So you have to operate this power system such a way that you should get a better result, not the final result. You should get a better result. So what is that better results? What is the things we have to consider here? Means now you see that one power system means you will be having what are the things, main things you will be having? Generation, transmission, and distribution. So loads are connected, and to reach the load demand or to satisfy the load demand, the power has to be transmitted over a long transmission line. So on the other side from the generating stations, right? Now this our optimal system operation focuses on generation side. Remember, this optimal system operation focus on your generation side. Understood. So whenever I am talking about on generation side, what is the important thing that we should keep it in mind on generation side? It is the generation which is happening through the generating plants or the power plants. So obviously this generation is happening because of various or different power plants. You know what you mean by power plants or generating stations. So this generating station may be hydroelectric power stations or coal-fired stations, that is thermal power stations, or nuclear power stations, or oil and gas generating stations, etc. There are different types of generations are there: hydro, thermal, nuclear, oil and gas, etc. These are the different types of generating stations are there, right? Now what about the cost of generation? Suppose if you want to produce 1 unit of power, 1 unit of energy, so what is the cost involved to generate this 1 unit, isn't it? Suppose if you take a hydroelectric generating station, the cost for producing 1 unit is different, and for nuclear it is different, thermal it is different, and oil and gas stations also it is different, isn't it? So the cost per unit production, the cost per unit production for different plants will be different. This is the first point. Number one. Number two, second important point is all these generating stations are not located at equidistance from the loads. Understood. So some generating stations are near to the loads, some generating stations are far away from the loads. So it is scattered. It is not centrally located. It is these generating stations are not centrally located so that it can distribute power on either side equally. No, it's not like that. It is not centrally located generating station. They are scattered. So therefore, transferring of power from one station to the distribution side, load side, obviously it will vary. It will vary, isn't it? Suppose if the transmission line is long, obviously losses will be more. Transmission losses will be more. If it is over a short distance, then the losses will be less. You know that one. Losses will be less. So because these losses are varying, so therefore this cost per unit of production will also vary. Understood? Because one first reason is different types of power plants are there. Second one is they are not centrally located, they are located at far away from the load centers, and they have to transmit the power over a long transmission line. So whenever they are transferring, some transmission losses are going to occur, isn't it? So depending on this one, so the cost per unit production will vary. These are the two main points. You should keep it in mind. So therefore, based on these two, cost per unit production will vary. So now we have to operate this power system economically. We have to operate this power system economically. That means when to operate nuclear power station, when to operate hydro power stations, when to operate oil and gas stations, when to operate thermal stations, etc. So it is not a single station. Thermal stations, if you take, there are so many thermal stations. So many hydroelectric power plants are there. So many, then nuclear power plants, okay, I cannot say so many. Yes, numbers are there. Similarly, oil and gas, it is there. So which stations to be operated, which stations to be operated at a given time so that it can be operated economically. So the entire focus in this chapter will be focused on economic considerations. Economic considerations. Now, what are the fuels that are available? Coal fired. In thermal, it is coal fired. It is there. Then nuclear, you know that one. So oil and gas, the fuel. What is that fuel? You know. And here, hydroelectric power plants. What happens? The operating cost is almost negligible. So it is a naturally available water is there. So only thing is they should know when to release the water and how much quantity they should release the water, etc. and all those things. So here the operating cost of these hydro plants are almost negligible. However, the operating cost is considered in thermal and nuclear stations, etc. Isn't it? So with this small introduction, so let us move. Already I covered all the points in this introduction. So let us look into what exactly we are going to see in this one optimal system operation. Now, by this time, you are aware that what we are going to study in this chapter, optimal system operation. That means the power plants or power system to be operated economically. That means economically means economy is coming into picture. Economy means it is a cost. It is a cost involved here. So what is that cost? How we are going to operate this power plant so that this is operated economically? We will see that one in this chapter. Okay, now you see this one optimal system operation. Not only I told these plants to be operated, these plants to be operated optimally such a way that it should satisfy some of the consideration. So what are those consideration? First, based on economy of operation, that is cost basis. This is economy of operation. Optimal system operation so should involve in solving or in considering the following problems. That is, first is economy of operation. Second, most important thing is system security. If system security is not taken care, then obviously there is a possibility of blackout may occur. Blackout may occur, so you may not get power supply. System security is more important. So whenever a fault occurs, how to take care of security, etc. This is also you should take care while operating optimally. Then the most important thing, emission at certain fossil fuel plants, that is especially in thermal plants, etc., and oil gas plants. So these emissions will be there, isn't it? And obviously nuclear also, it is nuclear radiation will be there. So that is also one type of the thing we have to consider. So emission also you should to consider when you are operating the system optimally. You have to consider emission. So emission should be minimum. Whatever the emissions that are coming out of these fossil fuels must be minimized. Then optimal release of water at hydro generation, etc. Optimal release. Suppose if you are having water, you have to produce the power constantly. So if you want to produce the power constant, so you have to see optimally, okay, how many gallons of water I should release now, how many gallons of water I should keep it in a reservoir, etc. So all those things they should take care of. So that means what? if you want to operate a power system optimally, these are the four things you should take care. One is on cost basis, it should be economical, then system security, then emissions should be minimum, then optimal release of water at hydro generations. And there are other parameters also are there. However, we will consider these things, these four things. Suppose if you try to operate the power plants on economical basis, then you may be compromising on system security, or you may be compromising with the emissions that are coming out from fossil fuel plants. Okay, economically it is at cheaper cost. You are getting it. You have seen some of the vehicles that are moving on the road, isn't it? They'll be using the cheap one, economy consideration. Considering that one, they are mixing something or they are using kerosene, isn't it? It is economical for them. But what about the emission? What about the emission that is coming out from those vehicles? Even we cannot see what is coming in front of us. That much thickness will be there, isn't it? Black, this one, smoke will be there in front of us. So that means what? Economically, it may be viable, but emission wise, it is not good for the environment, isn't it? So that means what? He has compromised on the emission, but in order to get the fuel at cheaper rate. Similarly, system security. So they may compromise. So to satisfy all these four multiple things, it is very difficult to satisfy the multiple things. So it is very difficult. So first aim is I want to operate the system at economical cost. That means at minimum cost. Then system security has to be taken care. Emissions to be minimum. Release of water at hydrogen generating station to be optimal. We cannot compromise on all the four things. So we are going to achieve economy. We may have to compromise with one or two of these things. We may achieve good result with economy and system security. Fine, but emission will be more. Understood? So that's why I'm telling it. So it will become a tedious task to achieve all these objectives simultaneously. Understood? Simultaneously. However, we have to do trade-off. We have to do trade-off between these four things, between these four objectives, such a way that it should be economical, system security is taken care, and emission is at some level, and release of water to hydrogen generation is at optimal level, so that the overall system operation will be optimal. Optimal means what? Better result. It is not the excellent or final result. That you should keep it. Optimal means better result. So in order to get the better result, so what you have to do, we have to do trade-off among these four things. Is it clear? So with this one, now let us see here. All the above, the same thing I've explained. It is a conflicting requirements, all the four. Suppose if you try to balance one thing, the other one may go out of balance, etc. So usually a compromise has to be made for optimal system operation among these four. That's it. How the compromise has to be made? It's not that you should completely neglect system security or you should completely neglect the economical considerations. No, should not compromise. You should compromise such a way that is compromise means I used another word, trade-off. Trade-off, you have to make it among these variables so that the system will be operated optimally. Now, if you take the modern grid, the conventional grid was different. Now the modernized grid is available, which is in which all the micro and mini hydro plants, etc. Micro grids are available. Renewable energy sources are integrated into the grid. So therefore, in this modern grid integrated system, have different types of generating plants, such as coal-fired thermal plants, hydel, nuclear, oil and natural gas. Now, in addition to this one, etc., I have written. So you may be having mini micro plants, hydel plants, or you may be having renewable energy sources power plants, that is solar power plant, or wind generation power plant, or biogas, biomass, etc. So all these things, renewable energy sources power plants are also now integrated into the grid, in the modern grid. Understood? So with these different types of power generating plants, so what happens? The capital investment, operation, maintenance costs are different for different plants. Obviously, I have explained it, isn't it? The investment cost will be different for thermal, investment cost for nuclear power plant will be different, for renewable energy sources it will be different, and also operation and maintenance cost also different, isn't it? Operation and maintenance cost, operation cost for hydro plant almost it is negligible if you take. However, operation cost for thermal and nuclear power plants we have to consider it. So it is different for different power plants. So the operation economics can again be subdivided into two parts. When you consider the economics of a power system, so this is subdivided into two parts. The first problem is economic dispatch. What is this economic dispatch? It deals with the determining the power output of each plant to meet the specified load. This is the economic dispatch. Now you see, assume some small system. You are having four generating stations and load is there. Load is connected. Suppose load demand is to say 1000 megawatt. Load demand is 1000 megawatt. So in order to meet this load demand of 1000 megawatt, these four power plants has to be operated. So this load demand must be supplied from these four stations. These four stations are different in nature. One may be thermal, one may be hydro, one may be nuclear, one may be renewable or etc. So out of these four generating plants, how to operate these four economically so that the power will be met. That is, the load demand will be met at minimal cost. Minimal cost. Understood? So therefore, this economic dispatch deals with determining the power output of each plant. How much power generation that should come out from each plant to meet the specified load demand. Generating 1, what is the power requirement? For generator 2, what is the power requirement? What is the generator 3 and 4? How much it should produce to meet the total load demand of 1000 megawatt? Understood. So this is what you have to find out, how much power each generator station has to produce to meet the given load demand. That is known as your economic dispatch. This is the one category of your economic operation. Then the second one is your optimal power flow. What is the difference between economic dispatch and optimal power flow? We'll see that one. Before going that one, as already said, so you have to check this one such a way that the overall fuel cost is minimized. Overall fuel cost will be minimized. Remember, this is the objective function in economic dispatch. What is economic dispatch problem? It deals with determining the power output of each plant to meet the specified load. This is the aim. What is the aim? Is to produce. So how much generator 1 has to produce, how much generator 2 has to produce, etc. to meet the load demand such a way that the overall fuel cost to be minimized. Remember this one, in economic dispatch, the aim is to minimize the overall fuel cost. Again, I am repeating it. In economic dispatch, what is the objective? Objective is to minimize the overall fuel cost. Understood? So this objective is achieved. This objective is achieved such a way that the generation is equal to load demand. Such a way that generation must be equal to the load demand. Under that constraint only, we have to find out overall fuel cost. Then the second one I was talking about, the optimal power flow. This is another problem in economic operation. What is this optimal power flow, which deals with minimum loss? So mainly this optimal power flow deals with minimum loss. If losses are minimum, so therefore whatever the power that is flowing, real and reactive power will be optimal. So that aim is to minimize the loss, wherein the power flow is optimized to minimize losses in the system. That's all. That means the power flow in the lines to be varied so that losses to be minimized. So in the optimal power flow, what is the objective function? Minimization of loss. Minimization of loss. So how it is achieved? By optimizing the power flow. Optimizing the power flow. So this is your second category of your economic operation, optimal power flow and economic dispatch. However, optimal power flow is your out of syllabus. So we will be studying at your level the economic dispatch. We are going to study only the economic dispatch. Understood? So this is the thing we are going to study. Optimal power flow, we are not going to focus here. Now, the main aim of economic dispatch problem is to minimize, already I told, to minimize the total cost of generating real power. So, what is the aim of economic dispatch problem? I said example I have taken 4 generating stations. Cost at generating 1 is different, cost for producing generation at 2 will be different, 3 and 4 are different. So what is the total cost of generation? Cost of generation means here it is real power. Please keep it in mind. So what is the total cost of generation? We have to add costs of all the individual plants. Whenever I say plants, it is generating stations, that is power plants. Please keep it in mind. Understood? So you have to minimize the total production cost. Here what is it is producing, what is the production here? Generating of real power. Minimize the total production cost or generating cost of real power at various stations while satisfying the loads and the losses in the transmission line. Isn't it? So total cost of generation to be minimized such a way that it should satisfy the loads as well as losses. Isn't it? Power system is what? Generation, transmission, distribution. Loads are connected on distribution side. So whenever generation is happening on one side and it has to transmit power over a long transmission line. So whenever it is transforming, line losses will be there. So then it has to meet the load. After subtracting these losses, so then only it is going to meet the load demand. So load plus losses is equal to your generation. Understood? Load plus losses is equal to your generation. So these are the basics. So obviously I have told several times, hydropower plants operating cost is almost negligible. There is no operating of hydropower plants because it is naturally available, water is available. Only investment cost will be there. For simplicity, we consider only the presence of uh, coal-fired coal-fired plants, that is thermal plants only. Understood? So in our studies, we are going to consider economic dispatch of thermal plants only. Here in this module, we are going to consider. Later, slowly, we will add hydro. We will add hydro power stations. So it will become hydrothermal generating stations. Hydrothermal generating station. That we will be studying it. Only these two cases. First considering only thermal, then considering hydrothermal. We will be studying in this module. Okay. So first only thermal plants will become dealing it. The objective of this thermal plant operation is to minimize the total generating cost of real power such a way that it should meet the load and the losses. Please remember this one. Clear? So now we will consider only thermal stations. Okay. So I hope till this point you understood. The aim is we are considering only thermal plants and our aim is to minimize the total generating cost such a way that it should meet the load and losses. Okay, fine. So let us take the categories cases. First one, optimal operation of generators on a bus bar. Please remember this optimal system operation totally majority depends on generation side. Understood? So optimal operation of generators on a bus bar. So under this one, so we are going to consider this one. The major component of generator operating cost is the fuel input per hour. So how much fuel you are giving it as an input per hour? is the main component, that is major component of your generator operating cost. Please remember these 2 points. For generating operating cost, the major component is fuel input per hour. If you have a diesel generator, how much fuel you have to put it in a diesel generator per hour? How much fuel it is required? Diesel is required per hour. So this is the major component of any generator operating cost. Now hope you understood what you meant by operating cost means it is fuel input per hour. That is a major component. Now, while the maintenance contributes only to small extent. Now you see here, the maintenance contributes only to small extent. That's why we are not considering the maintenance costs here. Understood? In the operating cost, we should consider the maintenance cost also. But here in thermal station, the maintenance contributes only to a small extent. The fuel cost is meaningful in case of thermal and nuclear station. That's what I said. Fuel cost is meaningful now. Whereas in hydro, what is the fuel? What are naturally available sources? So there is no cost involved in that one. Only investment cost will be there, isn't it? So that's why fuel cost will have meaning only in case of thermal and nuclear stations. Hydro station where the energy storage is apparently free. Now, the input to the thermal plants usually measured in BTU per hour. Input to the thermal plants, that is fuel input. What is a fuel input? The unit is British thermal units. So this is how it is measured. British thermal units per hour. British thermal units per hour. Understood. So here is a fuel input per hour. What is the fuel input unit? BTU. You see T is small, U is small, B is capital. British thermal units per hour. And how the output is measured? What is the unit output will be measured in megawatt? Obviously, you know that. So fuel input per hour is measured in British thermal units per hour and output is measured in megawatt. Okay, so what is the output is megawatt and input is the BTU per hour. Now we have to plot a curve based on this fuel input and the output. So this input output curve of a thermal unit is known as heat rate curve. Understood? So a simplified input. What is input? This is your input. This is your input, fuel input per hour. That is represented in British thermal units per hour input. What is output? Is your power output, megawatt. So this curve is shown like this. You see, this is output P in megawatt and this is fuel input per hour. You can write fuel input per hour, y-axis. That is nothing but British thermal units per hour. This is your input. So this input output curve will look like this. So will look like this. You can see here. I think it get disconnected now. Are you able to hear? I think now it's okay. Is it okay? Visible? Can anyone respond? Is it visible?
Yes, sir. Visible, sir.
Okay, okay. Thank you. I think it got disconnected in between. Okay, this is what I was explaining it. This curve, we can see it here. So this is output in megawatt and this is fuel input. See, please, they may be asking the questions, explain input output curve. So this is the input output curve. You have to draw and you have to explain this one. This is input and this is output. Input, what is input? Fuel input. So you see as output increases, so the fuel input also increases to some extent here. So this is your input output curve. Then heat rate curve. What is this heat rate? Is the ratio of fuel input in British thermal unit to the energy output. This is the actually heat rate curve. Heat rate curve is obtained from your input output curve. Understood? So because fuel input is British thermal units, isn't it? To energy output, what is heat rate? Is defined as heat rate is defined as the rate ratio of fuel input in British thermal units to the energy output in kilowatt. Energy is what? Watt hours, no? Energy will be the unit of energy is watt hour. So only thing is it is a unit, that is kilowatt hour, megawatt hour, etc. depending on the energy level. So therefore, here the heat rate is the ratio of fuel input to energy output, that is BTU per kilowatt hour, BTU per kilowatt hour to the output. So this is the curve we are getting it. Understood? You see the difference between the previous one and here. Previous one was like this: as output increases, the fuel input also increases. But what is the heat rate? What is the heat rate? What is heat rate? It is the ratio of fuel input to energy output. You see here, this is your ratio. BTU per kilowatt hour. Kilowatt hour, this one. This is the ratio. It is not fuel input here. So it is a heat rate. It is a ratio with respect to the output. So therefore, it is almost a reverse way, opposite to the inverse of your input-output curve you are going to get. So what happens to this heat rate? As output increases, the heat rate also gets reduced. Is it clear? That means fuel input to the energy output. So heat rate gets reduced as output increases. So next, coming back to it is the slope of the input output curve at any point, that you can say it in other words. So the reciprocal of heat rate is called fuel efficiency. The reciprocal of heat rate is called as fuel efficiency. What is reciprocal means what? So it is, you know, that reciprocal 1 over the ratio of this one is your fuel efficiency. Next, the heat rate curve is a plot of heat rate versus output. Already I have shown it. So this is what you have to explain it. Then coming back to fuel cost. Now you see here, fuel cost. Fuel input is different. Fuel cost is different. Fuel input is measured in British thermal units. Fuel cost is measured in rupees per hour. Rupees per hour. Understood? So converting the input output curve from BTU to hour to rupees per hour, this will result in fuel cost curve as shown in figure 3. Understood? So converting the input output curve from British thermal units per hour to rupees per hour. So we are going to have this fuel cost curve. So this x-axis is PI, megawatts. But what is on y-axis? It is fuel cost. So fuel cost is represented by C suffix I. C means it is a cost. CI means cost of ith generator. So what is the unit here? It is rupees per hour. Rupees per hour. And it is almost similar to your input curve. It is almost similar to your input curve. However, fuel cost increases much rapidly as compared to your input output curve. So please remember these waveforms, because while explaining this one, so heat rate curve is reverse of your fuel input or fuel cost curve. That way you remember it. Then finally, we'll have one more thing. So that is incremental fuel cost. So this incremental fuel cost curve is a measure of how costly it will be to produce the next increment of power. That is your incremental fuel cost. What do you mean by incremental fuel cost means what? If you want to produce the next increment of power, what is the cost? What is the cost involved? Suppose if you are producing 200 megawatt. Understood? Next time you want to produce 210 megawatt. Then what is the cost involved for the 10 megawatts? What is the cost involved for that delta value, that is 10 megawatt of extra generation, what is the cost involved? That is known as incremental fuel cost. Hope you understood. 200 megawatts is the normal one. Now we want to produce additional 10 megawatt, 210. So in order to produce this additional power of 10 megawatt, what is the additional cost involved? That is known as incremental fuel cost curve. So which is a measure of how costly it will be to produce the next increment of power. So that is the thing. With this one, in all practical cases, the fuel cost of generation I can be represented as a quadratic function of real power generation. So this is one of the important thing you should remember. How this incremental fuel cost curve we are going to get. So for all the practical purposes, the fuel cost of generator I, that is CI, fuel cost of generator I means CI, can be represented as a quadratic function. Quadratic function. What is your quadratic function? AX square plus BX plus C. Understood? Here the variable is x, ax square plus bx plus c. But here we have to write this one in terms of a real power generation. We have to write it in terms of real power generation. Understood? So in place of x, you write the generation. What generation? Real power generation. That is PG. PG means real power generation. Understood? So in place of x, the quadratic equation, write the generation parameter. Okay. Now see, consider this one. Now I have written this one. Only thing is I have written it in reverse way. So the fuel cost of generator I. What is CI? Is the fuel cost of generator I can be considered as a quadratic equation or quadratic function of real power generation. What is the quadratic function? Ax square plus bx plus c. I have written it in reverse way, that's all. So in place of x, use the generation. What is Ci? Ith generator. What is the generation at ith generator? Pgi. So this is x square plus bx. B is there, x is pgi plus c is constant. Some alpha I have taken it. Hope you understood this quadratic equation here in terms of real power generation. So this equation 1 is your fuel cost of generator I. If you want to find out the fuel cost of generator 1, replace I with 1. So C1 is equal to alpha 1 plus B1 into PG1 plus gamma 1 into Pg1 square. The unit is rupees per hour or rupees per, yeah, that's all, rupees per hour. Clear? Remember this equation one? Frequently we will be using this one, quadratic function. Some of the textbooks uses the different things. Here they will use AI, BI plus CI. Or here they will use AI, BI, CI. Whatever it is, depending on the textbook, they will use the different notations. Okay. Now taking the derivative of equation 1, take the derivative of equation with respect to the generation, real power generation. So that means taking derivative of Ci, dCi with respect to Pgi. So you are going to get this equation. You see dCi to dPgi. So what you are going to get? With respect to Pgi, you are taking derivative. What it will become? 2Pgi into gamma. 2Pgi into gamma, this term. And here, what is the derivative of Pgi into Bi? It is 1. Pgi is 1. So left out will be Bi. And this is a constant. Obviously, it will be 0. Understood? So taking derivative of equation 1, so we will be getting dCi by dPgi is equal to some equation. This I am going to call it as a lambda. This I am going to represent it as lambda. Call that as equation 2. The unit will be rupees per megawatt hour or kilowatt hour or just watt hour. Understood? So it is rupees per megawatt hour, lambda. Lambda is your incremental fuel cost. Lambda is your incremental fuel cost. That is nothing but DC to DPG, depending on the generator. Understood? Now, this equation 2 is known as incremental fuel cost. Understood? This is known as incremental fuel cost. So, using this equation, you can find out how much cost is required, how much cost is required to generate that extra 10 megawatt of power. I've taken example, no, 200 megawatt. If you want to increase that one to 210, that additional 10 megawatt, if you want to produce, what is the additional cost involved? That is nothing but your incremental cost. How to find out? Using this equation 2, that is DCI by TPG is equal to so and so into that is equal to lambda rupees per megawatt hour. So this is known as your incremental fuel cost, and this is cost. This is cost of producing real power generation at ith bus, and this is your incremental fuel cost. So already this is what I said. What do you mean by incremental fuel cost? Now what is the curve? How it appears? So that means it is incremental fuel cost versus power. You can see here. This is x-axis. Once again, it is PI in megawatt, PI in megawatt, and this is your incremental fuel cost, rupees per megawatt hour, y-axis. So how it will be? This is also almost similar to your input-output curve or fuel cost curve. Third one, figure 3 is there, no? That is fuel cost curve. It is almost similar to that one, isn't it? But for approximating this one with a linear fitting, so you will get a straight line. So that means you are going to get a slope of this curve. So that is your approximation of your linear cost. The dotted line which I have shown is your approximated linear cost. And what, but actually the cost curve will be varying like this. This is your actual cost. But after performing linear approximation, so taking that one, so this is your linear approximation, the straight line, dot line. Understood? Why dotted line? Now you see this one, isn't it? 2, this is a constant, Pj is a variable plus Ba is a constant. So it is like y is equal to mx plus c. So like that it is there, no straight line. So by with that approximation, we are getting it. This is your actual cost. That is fuel cost. And this is your incremental fuel cost, which is a linear one. We will be getting it. Okay. So these are the different curves we will be dealing it. So one is input output curve. Second one is heat rate. Third one is fuel cost. Fourth one is incremental fuel cost. So these are the 4 curves you should remember. And all for all x-axis is your output power in megawatt. Output power in megawatt. Only y-axis will vary depending on that one. Okay. So equation 1 and 2 you should remember. This is nothing but equation 1 is your cost, fuel cost. Equation 2 is incremental fuel cost. So, okay. Now, let us take, okay, still time is there. Economic dispatch, neglecting losses and no generator limits. This one we have to take it. Can I continue? Because, can I continue? Okay, fine. Okay, now till this point, now you understood what is fuel cost, what is incremental fuel cost, equation 1 and 2. Understood? So now with these two, we are going to deal it with the different cases. That means what? Without losses, with losses, transmission losses. So first we will be taking it without losses. How we are going to obtain economic dispatch? How we are going to solve the economic dispatch problem? So first case is economic dispatch, neglecting losses. Also, there are no limits on generators. Usually, whenever generating stations are there, limits will be provided. Okay, this is the minimum generation it should produce. and this is the maximum generation it should produce. So minimum generation, maximum generation limits will be provided on each generating station or generator. Understood? So first case will deal economic dispatch with no generator limits and neglecting the line losses, transmission line losses. This is the case one we'll be dealing it with. So under these circumstances, that is neglecting losses and assuming there are no limits on the generators, how we are going to solve this economic dispatch problem? So the simplest case of economic dispatch is the case when transmission losses are neglected. The model does not consider the system configuration or line impedances. Since losses are neglected, quite obvious, isn't it? Losses are neglected here. So therefore, the model, whatever you are going to develop, will not consider the system configuration or the line impedance. When you have to consider line impedances, whenever you are considering the losses, isn't it? Here we are neglecting it. So we are ignoring the line impedances also here. So therefore, such a way that the total generation is equal to total load demand. What is the equation I said while giving in the introduction? Total generation is equal to total load plus losses. This is the equation. Please remember, even in PSS lab, you have to verify the result which you are going to, this economic operation, you will be doing it by using the package which is available, My Power package. But theoretically, you have to justify the results, what you got it from that package. You have to justify the results. How we are going to justify the results? Load flow studies, economic operation, and short circuit studies. These three, you will be using the package, My Power package, to solve these three in PSS lab. The remaining things, you have to write the MATLAB coding. Okay, so this economic operation, you will be solving it using package. So after the package, okay, what you have to do in that package, you have to feed the input. You will get the output after executing. That's all. You have to do it. But only the critical thing in the using the packages, you should know how to enter or how to give the input, then how to execute it. These two things you should know it in that package. Understood? So therefore, total generation is equal to total demand plus losses. That is, generation is equal to PD is the load demand, PD plus losses. But in this case, we are neglecting the losses. We are neglecting the losses. So therefore, generation is equal to load demand, isn't it? Generation is equal to load demand. So that's what we are saying it here. After neglecting losses, the total generation is equal to the total load demand. That is PG. Total generation PG is equal to PD here. Now consider this figure. PD is the total load demand. PD is the total demand. And this is one power plant. This is your one power plant. And this is the second power plant, etc. This will be your nth power plant. That is nth generating station. This is first generating station, second generating station, and this is the nth generating station. And all these generating station will be supplying a load, total load of PD. Understood? Now, how we are going to write the equation here? What is C1? It is the, what is this C1? It is the fuel cost of generating station 1. Understood? What is C2? Fuel cost of generating station 2, etc. What is P1? Is the power output of generating station 1. What is P2? Power output of generating station 2, etc. So therefore, here we are saying total generation is equal to total load demand. From this pictorial representation, how we are going to satisfy this statement? Can anyone tell? And this cost function is assumed to be known for each plant. Cost function is assumed to be known for each plant. So based on this one, total generation. What is the total generation here? P1 plus P2 plus P3, etc. plus PNG is the total generation, isn't it? Equal to total load demand. What is the total load demand? PD. That means how you can write it in the form of equation P1 plus P2 plus P3, etc. plus PNG is equal to PD. Hope you understood this equation, isn't it? Now you see here, the aim is to find the real power generation for each plant. Now you see that one total generation is equal to total load demand, and what is the equation? How you are going to represent the equation from this picture, from this figure? P1 plus P2 plus P, etc. Png is equal to Pd. Now what is the aim is to find how much real power generation this plant 1 has to produce, how much real power generation the plant 2 has to produce, etc. How much this nth generator should produce to meet this load demand. Understood? How much generation the plant 1 has to produce, how much generation the plant 2 has to produce, etc. How much generation the nth generator has to produce to meet this load demand of PD. That is our aim, to find the power generation for each plant, such that the objective function, what is the objective function I told? It is a total production cost to be minimized. That is total generating cost to be minimized. So total cost, that is your objective function, is total cost of generation or total production cost to be minimized such a way that it should meet the load demand PD. So this is the thing. What is the aim is to minimize the total production cost by meeting this load demand. It has to meet this load demand. That is the constraint. It has to meet this load demand such a way that the production cost to be minimized. So in order to minimize, how much power each plant has to produce, that we have to find in this case. Understood. So objective function and all these things from here, I will continue in tomorrow's class, because now equations will start. And compared to load flow studies, here equations are very less. You will be comfortable, hope so. Any doubts till this point of economic operation? I will take it up. You can put it in the chat box or unmute yourself and you can discuss. No doubts, I think. Okay, fine. I'm going to end this meeting, today's class. So I'll continue this one in tomorrow's class. Thank you, one and all. Take care. Bye.